Okay, so you know that click-clacky desk toy,
Hmm.
the Newton's Cradle.
Yeah.
We're going to go on a deep dive today to understand what's really happening beyond that mesmerizing motion.
Right.
We've got some source material
Okay.
from a website all about physics simulations.
All right.
And get ready to uncover the math and modeling that brings this physics demonstration to life.
Yeah, it's amazing how something so simple can actually illustrate some of the most
Fundamental.
fundamental principles in physics.
So,
Yeah.
to get us started,
Okay.
let's picture the setup. You've got those identical metal balls hanging in a perfect row, just barely touching each other.
Right.
What happens when you lift one ball at the end and let it go?
Well, you get that satisfying click as it collides with the others, and then the ball on the opposite end swings out almost to the same height as the first ball was lifted.
Right.
Then it swings back, hits the row, and the process repeats.
Yeah, it's almost hypnotic.
It is.
What's going on behind the scenes? Our source material talks about the principles of conservation of momentum and energy. Can you unpack that for us?
Absolutely. So momentum is basically a measure of a moving object's oomph,
Okay.
like how much force it carries.
Right.
It depends on both the object's mass and its velocity.
Mm-hmm.
Energy, on the other hand, is the ability to do work like making those balls swing.
So these things, momentum and energy,
Yeah.
they don't just disappear during the collisions, right?
Exactly. They get transferred from one ball to the next.
Okay.
So when that first ball hits the line, its momentum and energy have to go somewhere.
Right.
They travel through the line as stationary balls
Uh-huh.
and ultimately cause that end ball to swing out.
That makes sense.
Yeah.
But our source material goes even deeper, right?
Yeah.
It actually gives us the equations used to simulate a Newton's cradle.
Right.
I'll admit I took one look at those and felt a little intimidated.
I can understand that they do look complex at first glance,
Mm-hmm.
but these equations actually describe the motion in a surprisingly elegant way.
Okay, talk me through it. I see symbols like the theta for the angle, omega for angular velocity, even good old G for gravity.
Right.
Yeah.
Instead of getting bogged down in individual symbols,
Okay.
let's focus on the bigger picture. These equations are all about describing the relationship between the ball's angle,
Yeah.
how fast it's swinging, and the forces acting upon it, things like gravity pulling it down and a tiny bit of air resistance slowing it down.
So it's not just about how fast the ball is swinging, but also how that speed is changing from moment to moment.
Right.
I'm starting to see how those equations make sense.
Yeah.
I'm still a bit fuzzy on how the simulation actually works.
Well, you have to remember that even though the motion appears smooth and continuous to our eyes, a computer has to break it down into discrete steps to model it.
Uh-huh.
Our source material calls these steps events.
Events.
Yes.
Okay, walk me through that.
Imagine you're watching a slow-motion video of the cradle.
Okay.
Each time two balls make contact, click, that's an event in the simulation.
Oh, so each click triggers the simulation to essentially pause and recalculate everything, right?
Precisely. And the source material outlines how those calculations work, bringing in concepts like mass and velocity, and how momentum gets exchanged during each impact.
So a heavier ball will have more of an impact, and a faster moving ball will transfer more energy.
Exactly. The equations in the source material account for all of that, calculating how the velocities of both balls change after they collide.
It's amazing to think that something we see as a smooth, continuous motion is actually being processed as a series of discrete events behind the scenes.
Right.
Makes you wonder what else we perceive as continuous that might actually be a bunch of tiny steps.
That's a great point, and it highlights one of the fundamental aspects of physics simulations. They allow us to approximate the continuous world in a way that computers can understand and work with.
Okay, but there's another piece to this puzzle, right?
Yeah.
The balls in a Newton's cradle don't just fly off in random directions.
Right.
Their movement is constrained.
Right.
How does the simulation handle that?
That's a key aspect, and our source material addresses it by using calculations for changes in position.
Okay.
These calculations make sure the balls stay on those circular arcs you see, rather than, say, taking off on a tangent.
So the math is making sure the simulated balls behave just like the real ones, swinging along those smooth, constrained paths.
Exactly.
This deep dive is giving me a whole new perspective on something I thought I already knew.
That's the beauty of digging deeper into the science behind everyday things. It opens up a whole world of understanding.
Yeah.
And we've only just scratched the surface.
I can't wait to hear more.
Yeah.
Shall we move on to part 2 of this deep dive?
Let's do it.
All right, we're back for part 2 of our Newton's Cradle deep dive, and I'm already feeling like I've learned so much.
It is fascinating stuff, isn't it? We've covered momentum energy collisions
Yeah.
and even how a computer simulation has to break down those seemingly smooth movements into individual steps.
Right, those events you were talking
Yeah.
about. It's like peeking behind the curtain of reality and seeing the code underneath.
Yeah.
But I have a question.
Okay.
What's the point of going through all this trouble to simulate something like a Newton's cradle?
Uh-huh.
I mean, it's cool to see how it works,
Right.
but what's the bigger picture here?
That's a great question. The real power of this kind of simulation and others like it
Okay.
is that it allows us to explore and understand complex systems in a safe and controlled environment.
Mm-hmm.
Think of it as a virtual laboratory for physics.
A virtual lab.
Yeah,
So instead of building a real Newton's cradle for every experiment, we can just tweak the parameters in the simulation and see what happens.
exactly. We can ask what-if questions
Okay.
and get answers without having to build a whole new physical setup each time.
Right.
For example, what would happen if we changed the mass of one of the balls? Would that change the overall pattern of motion?
That's a really cool thought. And we could test all sorts of crazy scenarios
Right.
that would be impossible or super dangerous in real life. Like, what if the balls were made of some super bouncy material instead of steel?
You got it. The possibilities are endless.
Wow.
And here's the best part. By comparing the results of these simulations to what we observe in the real world, we can actually improve our understanding of the underlying physics principles.
It's like a feedback loop, right?
Uh.
The simulation helps us understand reality,
Right.
and then observing reality helps us make the simulation even better.
Precisely. And that back and forth between the virtual and the real world is a cornerstone of the scientific process.
Okay.
It helps us refine our models,
Mm-hmm.
make better predictions, and ultimately gain a deeper understanding of how the universe works.
You know, it's funny, those equations that seemed so intimidating at first are starting to make a lot more sense now. It's like they're not just abstract symbols anymore, they're tools for describing the world around us.
They really are.
Yeah.
Those equations are the language that allows us to translate the complex dance of motion and forces into a form that we can analyze, understand, and even predict.
So for our listener out there who might be thinking, okay, this is all very interesting, but why should I care about the physics of a desk toy?
Yeah.
What would you say?
I'd say it's about more than just a desk toy.
Okay.
This deep dive into the Newton's cradle is a great example of how even the simplest things can hide a surprising amount of complexity.
Right.
It's a reminder that there's a whole universe of science happening all around us, even in the objects we might take for granted.
It's like finding hidden treasure in something you thought you already knew.
Exactly. And by understanding the science behind things, we can appreciate them on a whole new level.
Yeah.
Plus, who knows, maybe it'll spark your own curiosity to explore and ask questions about the world around you.
So to wrap up this part of our deep dive, what's the key takeaway you want our listener to walk away with?
I think the biggest takeaway is the power of simulations. They're not just for fun and games. They're incredibly valuable tools for scientists, engineers, and anyone who wants to explore complex systems and ask what-if questions.
Simulations give us the ability to experiment and tinker in ways that would be impossible or just way too expensive in the real world.
Right.
It's like having a universe sandbox at our fingertips.
Exactly.
Ready to move on to the final part of our deep dive.
I am.
Welcome back. We've journeyed deep into the heart of a Newton's cradle.
It's been quite a journey.
From the mesmerizing click-clack to the equations that govern its motion.
Right.
We've seen how energy and momentum dance between those perfectly aligned balls and how simulations allow us to explore the what-ifs of physics in a virtual world.
Yeah, it's like having a whole physics playground at our fingertips.
Now, as promised, we're going to leave you with a final thought, something to spark your imagination,
Okay.
keep those mental gears turning.
Like it.
So, remember how we talked about simulations allowing us to explore different scenarios?
Yeah.
Well, what if you were the one designing a Newton's cradle simulation?
Okay.
What would you change?
Oh, that's interesting.
What mysteries would you unravel?
Well, for starters, we've been working with the classic setup.
Right.
Identical balls, perfect alignment. But what if we shook things up a bit?
Okay.
Imagine one of the balls was significantly heavier than the others.
That's interesting. Wouldn't that throw off the whole system?
Yeah.
I mean, the heavier ball would probably move more slowly, but have a bigger impact when it hit the others.
Exactly. The pattern of swings would change dramatically.
Oh, wow.
The lighter balls might even bounce back with more speed.
Interesting.
It'd be a completely different dance of energy and momentum.
And speaking of changing things up, We talked about friction earlier.
Uh-huh.
In a perfect world, those balls would swing forever.
Right.
But in reality, they eventually slow down and stop.
Right. Friction is that ever-present force that steals a little bit of energy
Sure.
with every movement.
Yeah.
What if you incorporated a friction coefficient into your simulation?
Okay.
You can see how the cradle's swings gradually decay, ultimately coming to rest just like in the real world.
That's a great point. And here's another thought. What if we went beyond tweaking the balls themselves
Yeah.
and actually modified the cradle structure?
Oh.
Imagine a Newton's cradle that wasn't a straight line,
Uh,
but a curve or even a circle.
Now you're really thinking outside the box.
Yeah.
The balls wouldn't just swing back and forth.
Right.
They'd travel along the curve, colliding in a completely new and unpredictable pattern.
Wow.
It'd be a fascinating challenge to simulate the forces and interactions in such a system.
We've only just begun to explore the possibilities. Who knew that something as seemingly simple as a Newton's cradle could hold so much potential for exploration and discovery?
It just goes to show that curiosity and a little bit of imagination can unlock a universe of wonder, even in the most ordinary things.
Well said. And on that note, it's time to wrap up our deep dive into the Newton's cradle, but we hope this is just the beginning of your own explorations.
Keep questioning, keep experimenting, and never lose that sense of wonder.
Thanks for joining us on this fascinating journey. We'll see you next time on the deep dive.